December 7, 1941, 10 miles off the coast of Oahu, territory of Hawaii, Lieutenant Makatsura Hashimoto stood as torpedo officer aboard the Imperial Japanese Navy submarine I-24, observing through the pre-dawn gloom as the sub detached for its attack run toward Pearl Harbor. Hours later, as flames engulfed Battleship Row and smoke darkened the Hawaiian sky, Japanese officers across the Pacific celebrated what seemed an impossible triumph over the industrial giant they had been warned could never be defeated. Around Hashimoto, fellow officers expressed certainty that American naval power had been permanently crippled, that the technological superiority of Japanese armaments would ensure ongoing dominance. What none of them realized was that within those burning harbors lay the seeds of Japan's eventual destruction, and that the weapon which would sink their empire was already being loaded into American submarines, flawed beyond comprehension and dismissed by Japanese intelligence as evidence of U.S. technological inferiority. The calculus of Japanese naval defeat was being written not in the dramatic carrier engagements that would capture headlines, but in the grinding technical malfunctions of American torpedoes that would paradoxically enable the most lethal submarine campaign in naval history. The pattern of mutual misunderstanding and technological disdain had begun long before the first bombs fell on Pearl Harbor. The arrogance started on May 13, 1940, when a walk-in source, whose identity remains classified, provided the United States naval attaché in Tokyo with detailed intelligence about the Type 93 oxygen torpedo. This weapon, which Allied forces would later nickname the Long Lance, represented the pinnacle of Japanese naval engineering and a technological achievement that should have alarmed American naval planners. The specifications were extraordinary and, to Western eyes, almost unbelievable, ranges exceeding 22,000 yards at 48 knots and 33,000 yards at slower speeds, carrying a warhead of 1,080 pounds of high explosive. It was by far the most advanced torpedo in the world. The source supplied technical schematics, performance data, and operational doctrine detailing exactly how Japanese destroyers and cruisers would deploy the weapon in night surface engagements. The Office of Naval Intelligence carefully evaluated the report, forwarded it to the Bureau of Ordnance for technical assessment, and received back a conclusion that would prove catastrophically wrong. The Bureau dismissed the intelligence outright, reasoning that Japanese engineers could not possibly have developed a torpedo superior to American designs. The use of pure oxygen as an oxidizer, while theoretically feasible, was deemed too hazardous and too sophisticated for an Asian naval power to master safely. The report was filed and largely forgotten. Over the following months, as tensions with Japan escalated, this intelligence failure would cost thousands of Allied lives and dozens of warships. This dismissal reflected a broader prejudice that permeated Western military thinking about Japanese capabilities in the years leading up to war. Admiral Richmond Kelly Turner, who would later command amphibious forces in the Pacific and earn 4 Navy Crosses, had testified before Congress in 1940 that Japanese pilots were inferior due to alleged racial traits affecting vision and spatial awareness. These racist assumptions, presented as scientific fact, claimed Japanese aviators lacked the night vision needed for effective combat operations, that their technical training was inadequate compared to Western standards, and that their aircraft were inferior copies of Western designs. Army Air Force intelligence assessments in 1941 confidently asserted that the Zero fighter was derivative of obsolete American aircraft and would be no match for U.S. planes in combat. These assumptions cost American lives in the opening months of the war when Japanese pilots, flying technically superior aircraft and employing sophisticated tactical doctrine, dominated the skies over the Philippines, Wake Island, and the Dutch East Indies. The cost of this intelligence failure became clear almost immediately after Pearl Harbor. 7 American cruisers would be sunk by Type 93 torpedoes during the Pacific War. Heavy cruisers Quincy, Vincennes, Astoria, Chicago, and Northampton fell to long lances fired from ranges Allies considered impossible. 9 destroyers were sent to the bottom by these weapons. The fleet aircraft carrier Hornet, already crippled by dive bombers at the Battle of Santa Cruz, received fatal hits from destroyer-launched Type 93 torpedoes. Over 3,100 American sailors died directly as a result of long lance strikes. In most cases, the ships believed themselves safely beyond torpedo range when the weapon struck. Lookouts scanning the horizon saw no enemy vessels close enough to pose a threat. Captains maneuvering their ships assumed they were operating outside the danger zone based on intelligence estimates of Japanese torpedo capabilities. Then, long lances launched from cruisers and destroyers 15 or even 20 miles away slammed into hulls with devastating effect. The first encounter occurred at the Battle of the Java Sea on February 27, 1942. Dutch Rear Admiral Karel Doorman, commanding a makeshift force of American, British, Dutch, and Australian cruisers and destroyers, led his ships from Surabaya to intercept a Japanese invasion convoy approaching Java. The Allied force included heavy cruisers Exeter and Houston, light cruisers De Ruyter, Java, and Perth, and 9 destroyers representing 4 different navies, with 4 different tactical doctrines and significant language barriers complicating communication. Dorman was a competent officer thrust into an impossible scenario, commanding ships that had never operated together, with crews exhausted from months of continuous retreat, facing a Japanese force trained together for years under unified command and doctrine. The battle commenced at 1,600 hours when Japanese and Allied forces made contact visually, often beyond the range of most Allied vessels' visual detection. Japanese heavy cruisers Haguro and Nachi, the light cruiser Naka, supported by destroyers, maneuvered to bring their torpedo batteries to bear. At 1,633 hours, the light cruiser Naka launched 4 Type 93 torpedoes at 15,000 yards. Her escorting destroyers followed, launching 27 more torpedoes between 1640 and 1645 hours from 13,000 to 15,000 yards. At 1,652 hours, the heavy cruiser Haguro added 8 more torpedoes from an almost unbelievable range of 22,000 yards. The waters between the Japanese and Allied forces became filled with nearly 40 long lances running at depths of 12 feet, leaving no wakes, their oxygen propulsion systems producing no telltale bubbles. Allied lookouts and sonar operators, trained to detect torpedoes at much shorter ranges based on American and British torpedo capabilities, saw nothing until it was too late. At 1,713 hours, a Type 93 struck the Dutch destroyer Kortenaer midships. The half-ton warhead detonated against the destroyer's thin hull, breaking her back. Kortenaer jackknifed it and sank in under 2 minutes, taking most of her crew of 150 with her. Allied commanders, unable to comprehend torpedo attacks from such extreme ranges, concluded that submarines must be responsible. Throughout the remainder of the battle, Allied vessels maneuvered frantically to avoid what they believed were submarine-launched torpedoes, disrupting their formation and preventing coordinated attacks on the Japanese surface force. The battle raged for 7 hours as Dorman attempted repeatedly to reach the invasion transports and Japanese surface forces maneuvered to block him. The heavy cruiser exit took an 8-inch shell hit that penetrated her boiler room, reducing her speed and forcing her out of line. The British destroyer Electra was sunk by gunfire after making a gallant but futile torpedo attack. Dorman's force, reduced to 4 cruisers after the American destroyers withdrew due to fuel and ammunition shortages, continued searching for the invasion convoy through the night. At 2,325 hours, Japanese cruisers Haguro and Nachi, tracking the Allied force by radar, launched another spread of torpedoes from long range. At 2,332 hours, 1 Type 93 struck the light cruiser Java, the explosion igniting her magazines. Java blew apart and sank almost instantly, taking 512 of her crew of 600 with her. Minutes later, at 2,338 hours, another long lance struck Dorman's flagship Dieter. The torpedo detonated against the cruiser's ammunition magazines, triggering a catastrophic secondary explosion. Dieter broke in half and sank within minutes, killing Rear Admiral Dorman and 345 of his crew. The Battle of the Java Sea cost the Allies 2 light cruisers, 3 destroyers, and approximately 2,300 sailors killed. Japanese losses were 4 transports hit by stray torpedoes from their own cruiser, Megami, and minor damage to 1 destroyer. The invasion of Java proceeded without further interference. More significantly, the battle demonstrated the lethality of the Type 93 torpedo and the Allied inability to counter it. Yet, American intelligence analyzing battle reports and interrogating survivors refused to believe that surface ships had launched torpedoes from the ranges reported. The assessment remained that submarines were responsible, that Japanese surface torpedo capabilities were comparable to Allied weapons, that reports of extreme-range torpedo attacks or exaggerations by exhausted crews under extreme stress. This pattern continued at the Battle of Savo Island on August 9, 1942. One of the worst defeats in United States Navy history. At 0143 hours, Japanese float planes dropped parachute flares over the Allied cruiser force protecting the Guadalcanal landings, silhouetting the American and Australian ships against the night sky. Within minutes, Vice Admiral Genichi Mikawa's force of 5 heavy cruisers, 2 light cruisers, and 1 destroyer had closed to torpedo range. The battle lasted 32 minutes. When it ended, the Australian heavy cruiser Canberra was sinking, having taken 2 Type 93 torpedo hits in 24 8 inches shell hits. The American heavy cruisers, Quincy, Vincennes, and Itoria were all a flame and would sink before dawn. The heavy cruiser Chicago limped away with her bow blown off by a torpedo hit. Over 1,000 Allied sailors died that night, trapped below decks as their ships burned and sank, or killed instantly by torpedo detonations that broke their vessels apart. American survivors reported torpedoes coming from impossible ranges and directions, weapons that left no visible wakes, detonations from angles that suggested Japanese torpedoes could turn and maneuver after launch. Intelligence officers dismissed these reports as combat confusion, the natural tendency of survivors to exaggerate threats and rationalize defeat. The assessment remained that Japanese torpedoes were roughly equivalent to American weapons. Perhaps slightly better in certain characteristics, but not dramatically superior. This willful blindness to evidence would persist until 1943, when examination of intact Type 93 torpedoes recovered from sunken Japanese destroyers finally confirmed that the pre-war intelligence had been accurate. By then, thousands of Allied sailors had died and dozens of ships had been lost to a weapon American intelligence insisted couldn't exist. This willful blindness to Japanese technological capabilities mirrored Japanese attitudes toward American weapons, creating a symmetrical intelligence failure that would have far different consequences for the two powers. As American submarines began war patrol operations in December 1941, Japanese naval intelligence officers compiled reports on early American torpedo attacks with barely concealed satisfaction and growing confidence that the submarine threat was manageable. The reports documented failure after spectacular failure, malfunctions so consistent that they suggested fundamental flaws in American torpedo design and American submarine training. On December 14, 1941, just 7 days after Pearl Harbor, the submarine Seawolf, commanded by Lieutenant Commander Frederick Warder, encountered a Japanese freighter anchored off the southern coast of Mindanao in the Philippines. Ward maneuvered his boat into perfect attack position, range 3,000 yards, target stationary and unescorted. He fired 8 Mark 14 torpedoes, the standard weapon of the American submarine force, each costing over $10,000 and representing months of production effort. 7 torpedoes missed entirely, passing beneath the target or running wild. The 8th struck the freighter squarely amidships. Seawolf's crew heard the dull clang of metal striking metal through the submarine's hull. No explosion followed. The torpedo, its warhead, packed with 643 pounds of Torpex explosive, had hit the target directly and failed to detonate. The freighter, its crew alerted to the submarine's presence, got underway and escaped while Seawolf dove to avoid the depth charge attack that never came because the Japanese vessel had no anti-submarine weapons aboard. On December 24, 1941, Christmas Eve, the submarine Sargo, commanded by Commander Tyr Jacobs, encountered 4 Japanese cargo ships off the coast of Indochina, steaming in a loose convoy without escort. Jacobs maneuvered his boat into textbook attack positions, firing 3 torpedoes at each of 4 targets, 12 torpedoes total, from ranges between 1,000 and 2,000 yards. The conditions were perfect. The sea was calm, visibility excellent, the targets making steady courses and speeds. Every torpedo either missed entirely or malfunctioned. Not a single explosion. Jacobs observed through his periscope as torpedo after torpedo passed beneath targets or struck and failed to explode, or exploded prematurely without causing damage. He fired his final attack, the last 4 torpedoes in his forward tubes, at a large cargo ship that had stopped and was lowering boats to investigate what was happening. All 4 torpedoes ran beneath the stationary target. Sargo returned to Manila Bay on December 30, her crew demoralized, having expended all 24 torpedoes aboard without sinking a single ship. Commander Jacobs filed a scathing after-action report stating unequivocally that his torpedoes were running far deeper than their set depths, passing harmlessly beneath targets. The Bureau of Ordnance in Washington, responsible for torpedo development and production, dismissed his complaints with barely concealed contempt. The problem, Bureau officers insisted, lay with submarine commanders who didn't understand proper torpedo maintenance, with crews who weren't performing correct pre-launch procedures, with captains who couldn't execute proper attack approaches. The Bureau's position was that the Mark I torpedo was the most sophisticated, most thoroughly tested weapon in the American arsenal, and that any failures were due to operator error, not design flaws. This position would be maintained with bureaucratic obstinacy for nearly 2 years while American submarines fired thousands of defective torpedoes and Japanese merchant ships steamed safely to port with American torpedoes lodged unexploded in their hulls. Japanese intelligence officers monitoring American submarine radio traffic, decrypting American operational messages through partial breaks in American codes, and interrogating crews from sunken submarines, compiled detailed reports on American torpedo failures. These reports reached Imperial Naval General Headquarters in Tokyo by early 1942 and were analyzed by intelligence staff officers who drew precisely the wrong conclusions. American torpedoes, they reported, were primitive weapons plagued by fundamental design flaws. American submariners were poorly trained and lacked the aggressive spirit necessary for effective combat operations. The vaunted American industrial capacity was producing weapons that didn't work, ships that were inferior to Japanese vessels, equipment that broke down under combat conditions. This assessment based on accurate observation of American failures, but fundamentally wrong in its interpretation of what those failures meant, would prove to be one of the most catastrophic intelligence judgments in modern warfare. Throughout 1942, the pattern repeated itself with numbing regularity across the Pacific. American submarines stalked targets, maneuvered into attack positions, fired torpedoes that should have guaranteed kills, and achieved nothing. The statistics told the story. In 1942, American submarines in the Pacific fired 1,442 torpedoes at Japanese targets. They claimed to have sunk 211 ships totaling nearly 1.3 million tons. Post-war analysis of Japanese records conducted by the Joint Army-Navy Assessment Committee revealed the true figures were 109 ships totaling 41,871 tons, barely 3% of the claimed tonnage. Submarine commanders filed report after furious report documenting torpedoes that ran too deep, that exploded prematurely without causing damage, that struck targets directly and refused to detonate. Japanese merchant captains began reporting American torpedoes lodged unexploded in their hulls while their ships limped safely into port for repairs. The torpedoes carefully removed by Japanese ordnance personnel who examined them with professional interest and growing confidence. These reports reinforced Japanese confidence that the American submarine threat was manageable, that convoy protection resources could be allocated elsewhere, that the merchant fleet could operate with minimal escort and still maintain the logistics pipeline that fed Japan's war economy. This confidence shaped strategic decisions about resource allocation, shipbuilding priorities, and anti-submarine warfare doctrine. Resources that might have gone to building escort vessels, developing effective sonar and radar, training anti-submarine warfare crews, instead went to battleships and fleet carriers for the decisive battle that Japanese naval doctrine anticipated. The assumption that American submarines were toothless would persist until late 1943, by which time it would be too late to implement the convoy protection and anti-submarine measures that might have preserved Japan's merchant marine. The truth was far more complex and ultimately far more ominous for Japan than intelligence assessments suggested. The Mark I 14 torpedo designed during the Great Depression when testing budgets were almost non-existent suffered from 3 catastrophic defects that masked each other and made diagnosis extraordinarily difficult. Understanding how these defects were finally identified and corrected requires understanding how the torpedo was designed, tested, and deployed. The Mark I 14 torpedo was designed starting in 1931 to replace the Mark X, a World War I-era weapon that equipped older S-class submarines. The Mark I 14 was intended for the new fleet submarines then under construction. Boats like Gato, Wahoo, and Tang that would form the backbone of the American submarine force. The design specifications were ambitious. The torpedo would be 20 feet 6 inches in long, weigh 3,000 pounds, carry a 643 pounds Torpex warhead, and achieve a range of 4,500 yards at 46 knots or 9,000 yards at 31.5 knots. It would be guided by a sophisticated gyroscope system and would run at a set depth controlled by a hydrostatic mechanism. Most ambitiously, it would be equipped with the Mark 6 exploder, a magnetic influence device that would detonate the torpedo beneath the keel of enemy ships, breaking their backs and ensuring kills. The Mark 6 exploder represented cutting-edge technology for its era. Instead of requiring a direct hit on the target's hull, the Mark 6 would detect changes in the Earth's magnetic field caused by a ship's steel hull passing overhead. When these magnetic changes reached a certain threshold, the exploder would fire, detonating the torpedo beneath the target where the explosion would be most effective. German U-boat had experimented with magnetic exploders in World War I with mixed results. British torpedoes used magnetic exploders with moderate success. The American Mark 6 was designed to be more sensitive, more reliable, more sophisticated than any previous magnetic exploder. The problem was testing. A Mark 114 torpedo in 1931 cost over $10,000. Equivalent to roughly $200,000 in current purchasing power. In the depths of the Great Depression, with naval budgets slashed to the bone and Congress investigating every expenditure, the Navy was extraordinarily reluctant to spend money destroying expensive torpedoes in live fire tests. Instead, the Mark 114 was tested using exercise heads, dummy warheads that could be recovered after test firings. These exercise heads were filled with water and air to approximately match the weight distribution of the combat warhead, then fired at targets or through measured ranges to verify depth control and gyroscope function. After firing, the torpedoes were recovered, examined, and reused. This testing protocol seemed sensible and economical. It was also completely inadequate. The exercise head, while approximating the weight of the combat warhead, had a different weight distribution. The combat warhead contained 643 pounds of high explosive in the forward section of the torpedo. The exercise head contained water distributed throughout the warhead section. This difference in weight distribution affected the torpedo's trim and hydrodynamic characteristics in ways that wouldn't become apparent until combat use. Furthermore, no live fire tests were conducted against actual target ships to verify that the exploder would function properly under combat conditions. The Mark 6 magnetic exploder was so secret that submarine commanders weren't allowed to examine it or understand how it worked. The entire system was accepted for combat use based on mathematical calculations, laboratory tests, and exercise firings that never duplicated actual combat conditions. The first effect was depth control. The torpedo ran 10 to 11 feet deeper than its set depth because the depth control mechanism had never been properly tested. With the heavier combat warhead, when engineers increased the warhead weight during final development, adding 80 pounds of additional explosive to increase lethality, they failed to recalibrate the hydrostatic depth sensor. Additionally, this sensor was poorly positioned on the torpedo's body, where water flow created pressure variations that confused the mechanism. As the torpedo accelerated to combat speed, water flowing over the hull created a pressure drop at the sensor location through Bernoulli's principle, the same effect that creates lift on aircraft wings. The depth mechanism, detecting this pressure drop, interpreted it as the torpedo being too shallow and responded by trimming the torpedo to run deeper. The faster the torpedo ran, the greater this effect became. Every Mark 14 fired in combat in 1941 and 1942 ran far beneath its intended depth. Torpedoes set to run at 10-foot depth, designed to strike a ship at the waterline, actually ran at 20 to 25-foot depth, passing harmlessly beneath targets. A simple laboratory test, immersing a non-moving torpedo in a pool of static water, would not reveal this problem because there was no water flow to create the pressure effect. Dynamic tests using exercise heads with depth recorders showed the torpedo running at the correct depth, but the depth measuring device in the exercise head suffered from the same placement problem and gave consistent though incorrect measurements. The defect was real. It affected every torpedo fired, but the testing protocol was incapable of detecting it. This defect alone would have caused massive problems, but it was masked by the second defect, the magnetic exploder. The Mark 6 was designed to detonate when it detected the magnetic signature of a ship's steel hull overhead. In theory, This was brilliant. The torpedo would run beneath the target and explode under the keel, where the shockwave and gas bubble would be most effective at breaking the ship's back. In practice, the Mark VI proved wildly unreliable. The Earth's magnetic field varies significantly with location affected by latitude, local geology, and other factors. The Mark VI had been tested near the Naval Torpedo Station in Newport, Rhode Island, where the magnetic field strength and orientation were suitable for its operation. In combat in the Pacific, operating near Java, the Philippines, Guadalcanal, and Japan itself, magnetic field characteristics were entirely different. The Mark VI calibrated for Newport failed catastrophically in the combat environment. Some torpedoes exploded prematurely, detonating 50 or 100 yards before reaching their targets when the magnetic trigger detected the target's magnetic signature at too great a range. These premature detonations did minimal damage, merely alerting the target that it was under attack and allowing evasive action. Other torpedoes passed beneath targets and failed to explode at all because the magnetic field changes weren't sufficient to trigger the exploder in the actual operating environment. Submarine commanders watching through periscopes as perfect shots resulted in premature detonations that did no damage grew increasingly frustrated. They reported these malfunctions repeatedly, filing detailed after-action reports with recommendations that the magnetic feature be disabled. The Bureau of Ordnance responded by insisting that the problem was improper maintenance, incorrect calibration procedures, or failure to follow proper operating protocols. The deep running defect and the magnetic exploder defect masked each other in a way that made diagnosis extraordinarily difficult. Torpedoes running too deep wouldn't trigger the magnetic exploder because they passed too far beneath the target's magnetic signature. Getting the torpedoes to run at the correct depth would presumably fix the exploder problem, but when depth was finally corrected in mid-1942, the magnetic exploder continued to malfunction and the contact exploder revealed its own catastrophic defect. The third defect was in the contact exploder mechanism itself. The Mark VI incorporated both magnetic and contact firing systems in a single unit. If the magnetic system failed to detonate the torpedo as it passed beneath the target, the contact exploder would theoretically fire when the torpedo struck the target's hull. This contact system used a firing pin design that had worked reliably in older torpedoes that ran at slower speeds. The Mark X, which the Mark 114 replaced, achieved a top speed of 36 knots. The Mark VI contact exploder had been designed and tested for that speed regime. The Mark 114 ran at 46 knots, 28% faster, and nobody had tested whether the contact exploder would work properly at the higher impact velocity. When a torpedo traveling at 46 knots strikes a steel hull, the deceleration is nearly instantaneous and extraordinarily violent. The firing pin in the Mark VI contact exploder was relatively heavy, and it was held in place by a spring that had to be stiff enough to prevent premature firing during normal torpedo handling, but weak enough to allow the pin to move when the torpedo struck a target. At the Mark 114's high impact velocity, particularly when the torpedo struck at a 90 degrees angle as submarine commanders were trained to shoot, the sudden deceleration caused the firing pin to bind in its housing before it could strike the detonator cap. The friction forces on the pin during deceleration exceeded the spring force that was supposed to drive it forward. The result was that perfect shots, direct 90 degrees angle hits exactly as taught in submarine school were most likely to be duds. Only oblique angle hits where deceleration was more gradual allowed the firing pin to function properly. This defect had actually been discovered and corrected in older torpedo models back in 1922. The solution had been to use a stiffer spring and lighter firing pin components. But when the Mark VI was designed, incorporating the new magnetic exploder function, the earlier lesson was apparently forgotten. The contact exploder inherited the old firing pin mechanism without any testing to verify it would work at the Mark 14's higher speed. Japanese merchant ships began arriving in port with American torpedo dents and sometimes with unexploded American torpedoes actually lodged in their hulls. The ultimate humiliation for American submarine crews who had executed perfect attacks. The cost in American lives and lost opportunities during 1942 and early 1943 was staggering. Submarine commanders stalked targets for hours or days, maneuvering into ideal attack positions at great risk from Japanese anti-submarine forces, fired spreads of torpedoes that should have guaranteed kills, and watched in anguish as nothing happened, or as premature detonations merely alerted targets without sinking them. The morale impact on submarine crews was severe. Men who had trained for years to become submarine warriors, who took their boats into harm's way despite knowing that submarines had the highest casualty rate of any American combat arm, who risked their lives executing perfect attacks, saw those attacks fail because their primary weapon was fundamentally defective. Lieutenant Commander Frederick Warder, commanding the submarine Seawolf, encountered an 8,000-ton Japanese transport at anchor in Talamo Bay in the Philippines in January 1942. The target was stationary, unescorted, perfect conditions for an attack. Ward fired 4 Mark 114 torpedoes from point-blank range. He heard 4 dull clangs as they struck the target's hull. None exploded. The transport, alerted to Seawolf's presence but undamaged, got underway and began zigzagging while calling for air support. Ward reloaded his tubes with older Mark 10 torpedoes, weapons dating to World War I that lacked the Mark 114's sophisticated features, but which worked. The first Mark 10 exploded against the transport's stern. Ward fired another which struck amidship and broke the ship's back. The transport sank in minutes. Warder's after-action report stated bluntly that the Mark 114 was defective and should be withdrawn from service immediately. The Bureau of Ordnance not only ignored his recommendation, but suggested in its response that where needed additional training and proper torpedo maintenance procedures. Lieutenant Commander Eugene McKinney, commanding the submarine Tamber, fired 8 torpedoes at a Japanese destroyer in April 1942 from a range of 800 yards. He heard 8 dull metallic clangs as they struck the destroyer's thin hull plating. None exploded. The destroyer, now fully aware of Tamber's position and bearing, counterattacked with depth charges that came close enough to shatter light bulbs throughout the submarine and cause leaks in multiple systems. Tamber barely escaped, surfacing after dark in heavy seas to ventilate the boat and make repairs. McKinney recovered 8 of his torpedoes floating on the surface, their warheads unfired, examined them carefully, and radioed a blistering report to Pearl Harbor detailing exactly what he had observed. The Bureau of Ordnance response accused him of improper torpedo handling and poor maintenance practices that had caused the exploders to malfunction. Japanese intelligence intercepts of these communications, partial decryptions of American submarine radio traffic, and reports from agents in American-controlled ports noted that American submarine commanders were blaming their own weapons for combat failures. This was interpreted as clear evidence of American technological inadequacy and poor training. Japanese anti-submarine doctrine, never prioritized because intelligence assessments insisted submarines were not a serious threat, remained focused primarily on protecting naval task forces rather than merchant convoys. Destroyer escorts and patrol craft designed primarily for surface combat lacked effective sonar, adequate depth charge equipment, and tactical doctrine for hunting submarines. Japanese naval construction priorities focused on battleships and fleet carriers for the decisive battle, not on unglamorous escort vessels for convoy protection. The breaking point for the torpedo crisis came in 2 incidents during June and July 1943 that finally forced the Bureau of Ordnance to acknowledge reality. On June 10, 1943, the submarine Trigger, commanded by Commander Roy Benson, encountered the fleet aircraft carrier Ho, one of Japan's most valuable capital ships and a critical asset for Japanese naval aviation. Benson executed a textbook approach, maneuvering Trigger into perfect attack position at a range of 1,200 yards, firing range so close that missing was virtually impossible. He fired 6 torpedoes in a carefully calculated spread designed to ensure multiple hits regardless of the target's evasive maneuvers. 2 torpedoes missed due to Ho's emergency turn. 1 exploded prematurely 80 yards short of the target. The underwater detonation visible through Trigger's periscope, but causing no damage. 1 was a dud, striking Ho's hull and failing to explode. 2 torpedoes hit and detonated properly, causing moderate damage that reduced Ho's speed and started fires. Ho, protected by destroyer escorts that immediately began depth charge attacks on Trigger's probable position, limped away for repairs instead of sinking. The carrier underwent emergency repairs at CBO and was back in service within 6 weeks. She would survive to participate in the Battle of the Philippine Sea on June 19, 1944, where her aircraft would attack American carriers before she was finally sunk by submarine Archerfish. That's single torpedo failure on June 10, 1943, 2 torpedoes out of 6 failing to function as designed, cost the United States a fleet carrier at a time when every carrier mattered desperately in the balance of naval power in the Pacific. The loss of Ho in June 1943 instead of June 1944 might have prevented her aircraft from participating in combat actions that killed American sailors and aviators. The torpedo failures had strategic consequences that rippled through the entire course of the war. The second incident proved even more definitive in forcing the Bureau to act. On July 24, 1943, Lieutenant Commander Lawrence Daspit, commanding the submarine Tinosa on her second war patrol, spotted the 19,250-ton whale factory ship Tonin Maru No. 3 alone and unescorted south of Truk. This represented a submarine's dream target. The ship was enormous, slow, defenseless, and carried critical whale oil for Japanese industry. Whale oil was used in the production of nitroglycerin for explosives, in food products, and in various industrial processes. Sinking her would inflict both immediate material loss and longer-term economic damage. Daspit maneuvered Tinosa into attack position at a range of 4,000 yards and fired 4 torpedoes. He observed 2 hits that stopped the ship dead in the water. Daspit immediately fired 2 more torpedoes. Both hit. 6 torpedo hits should have been more than sufficient to sink any merchant vessel. Tonin Maru No. 3 remained afloat, dead in the water, but refusing to sink. With no enemy anti-submarine forces in sight, Daspit had time. He carefully maneuvered Tinosa into a textbook perfect position, 875 yards directly a beam of the target where missing was impossible, and every torpedo would strike at the optimal 90 degrees angle. He fired 9 more torpedoes, observing each one carefully through his periscope, despite Japanese machine gun fire from the target ship. All 9 hit the stationary target squarely at the optimal angle. None exploded. Daspit heard the dull thuds of impact through Tinosa's hull. Not a single torpedo detonated. Daspit, suspecting he had received a bad production batch from the torpedo factory, kept his last torpedo unfired for analysis by experts back at Pearl Harbor and cleared the area before Japanese aircraft could arrive. He had fired 15 torpedoes at a perfect target under ideal conditions. 6 had hit and failed to explode. 9 had hit and failed to explode. None had exploded prematurely or run wild. All had functioned perfectly except for the one critical function of exploding. Rear Admiral Charles Lockwood, Commander, Submarines Pacific Fleet since January 1943, recognized that Daspit's experience represented a controlled experiment conducted under combat conditions. Lockwood was himself an experienced submariner, having commanded submarines in the 1920s and 1930s before moving to senior positions. He had listened to 2 years of his submarine commanders reporting torpedo failures. He had watched as the Bureau of Ordnance blamed every failure on operator error, poor maintenance, or improper attack procedures. He had seen the morale impact on submarine crews who were risking their lives executing perfect attacks only to have their weapons fail. He had read the intelligence reports suggesting Japanese merchant ships were arriving in port with unexploded American torpedoes lodged in their hulls. He now had proof documented in Daspit's patrol report with photographs and detailed observations that the contact exploder was fundamentally defective. Lockwood ordered immediate testing. His staff constructed a testing range where dummy warheads could be dropped from a pier crane onto steel plates positioned at various angles to simulate torpedo impacts. The tests revealed that the firing pin mechanism bound and jammed at high impact velocities, particularly at 90 degrees impact angles. The heavier the firing pin and the stiffer the deceleration, the more likely the binding became. Direct 90-degree hits, the supposedly perfect shots that submarine commanders were trained to take, generated such sudden deceleration that the firing pin couldn't move fast enough to strike the detonator cap. The contact exploder was fundamentally defective. And the defect became worse with perfect shooting. The solution came from an unexpected source. During the Pearl Harbor attack, American anti-aircraft fire had shot down several Japanese aircraft. Engineers examining the wreckage at the Naval Air Station discovered that the propeller blades were made from a lightweight aluminum alloy rather than the steel used in American propellers. This material, strong enough for its purpose, but significantly lighter than steel, suggested a solution to the firing pin problem. If the firing pin were made from lightweight aluminum instead of steel, it would have less inertia during deceleration and would be less likely to bind. Tests confirmed the theory. By September 1943, 21 months after Pearl Harbor, modified torpedoes with aluminum firing pins and other design improvements began reaching submarines. At Pearl Harbor and Fremantle, the transformation in American submarine effectiveness after September 1943 represented one of the most dramatic capability shifts in naval warfare history. From December 1941 through August 1943, American submarines had operated with their primary weapon barely functional. 3 separate catastrophic defects, each masking the others, had rendered the Mark 114 torpedo unreliable at best and completely useless at worst. Submarine commanders had adapted as best they could, setting torpedoes to run at shallower depths to compensate for depth control problems, deactivating magnetic exploders against orders to prevent premature detonations, attempting oblique angle shots instead of the perfect 90 degrees angles they had been taught. But these were workarounds, temporary measures that addressed symptoms without curing the underlying disease. After September 1943, with all 3 defects corrected, the Mark 114 became the weapon it had been designed to be. Depth control now worked properly. The magnetic exploder had been permanently deactivated in favor of contact detonation only. The contact exploder now functioned reliably at all impact angles and velocities. Submarine commanders who had learned their trade in the School of Hard Experience, who had survived 2 years of combat despite defective weapons, now possessed torpedoes that actually worked. The effect on Japanese shipping was immediate and catastrophic. Japanese naval planners observing early American submarine operations through 1942 and early 1943 had concluded that the submarine threat was manageable. Convoy protection resources were allocated primarily to protecting naval task forces and troop convoys rather than merchant shipping. Destroyer escorts and patrol craft focused on protecting battleships and carriers. Anti-submarine warfare doctrine emphasized protecting high V-value military targets. The merchant fleet, carrying raw materials from conquered territories to Japan and carrying finished military goods from Japan to forward bases, operated with minimal escort under the assumption that American submarines weren't effective enough to pose an existential threat to Japanese maritime logistics. This assessment proved catastrophically wrong once American torpedoes began working reliably. The submarine flasher, commanded by Commander Reuben Whittaker, intercepted a convoy off into China on December 22, 1944. Whittaker maneuvered his boat into attack position and fired 6 torpedoes at 3 tankers. All 6 torpedoes functioned perfectly. 3 tankers, the 10,000-ton Omarosan Maru, the 9,200-ton Arita Maru, and the 9,200-ton Ottawasan Maru, carrying critical fuel oil from the Dutch East Indies to Japan, went to the bottom in less than 20 minutes. In a single attack, Whittaker had sunk over 28,000 tons of shipping and sent hundreds of thousands of gallons of irreplaceable fuel to the ocean floor. The submarine Barb, commanded by Commander Eugene Fluckey, achieved even more spectacular results. On her 11th war patrol in 1945, Barb sank 17 ships totaling over 96,000 tons, setting a record for tonnage sunk on a single patrol that would never be exceeded. On June 23, 1944, operating off the China coast, Fluckey executed an attack on a convoy in Namuan Harbor. In just 54 minutes of furious action, Barb sank 4 ships totaling over 15,000 tons. These were not lucky hits or random successes. These were precisely executed attacks using weapons that now worked as designed, delivered by submarine commanders who had learned through bitter experience exactly how to employ them to maximum effect. The statistics documented the transformation. In 1942, American submarines fired 1,442 torpedoes and claimed 211 ships for 1.3 million tons. Actual results: 109 ships for 41,871 tons. In 1943, as the torpedo problems were gradually corrected, submarines fired 3,937 torpedoes and sank 284 ships for 1,349,473 tons. In 1944, with fully functional torpedoes, submarines fired 692 torpedoes and sank 492 ships for 2,388,000 tons. The effectiveness improvement was roughly tenfold once the torpedoes began functioning properly. By the end of the war, American submarines had sunk 1,178 Japanese merchant vessels, totaling 553,491 tons, representing 54.6% of all Japanese shipping losses from all causes. More critically, they had sunk 201 naval vessels, including the aircraft carrier Shinano, the largest carrier ever built. At 72,000 tons displacement and the largest warship ever sunk by a submarine, the toll on Japan's economy was catastrophic and fundamentally altered the strategic balance in the Pacific. Japan was an island nation, utterly dependent on seaborne logistics, raw materials from conquered territories. In Southeast Asia, China, and the Dutch East Indies had to be shipped to Japan for processing. Finished military equipment had to be shipped from Japan to forward bases and combat zones. Food imports were essential to feed the population. Oil from the Dutch East Indies was critical to every aspect of the war economy and military operations. By January 1945, the Japanese merchant fleet had been reduced to barely a quarter of its December 1941 strength. Tankers carrying oil from the East Indies were being sunk faster than they could complete round trips. Cargo ships, bringing raw materials, were going to the bottom with their holds full. Food imports had declined to the point that rationing in Japan approached starvation levels. The industrial repercussions reverberated through every aspect of Japan's war effort. Oil refineries on the home islands ceased operations due to shortages of crude from the East Indies. Japan's petroleum output, which had never fully met military demands even with imports from the Dutch East Indies and Borneo, collapsed to minimal levels. Steel mills shut down due to a lack of iron ore and coking coal. Aircraft factories halted production because of shortages of aluminum, which had to be imported as Japan had virtually no domestic production. Pilot and sailor training programs stalled from insufficient fuel. Naval vessels remained idle at pier or anchored due to oil scarcity. The combined fleet, once the third largest navy in the world and a force that had defeated the Russian Navy at Tsushima and dominated the Western Pacific in 1942, was immobilized by fuel shortages. Army divisions in China, Southeast Asia, and Pacific Islands deteriorated from lack of supplies and reinforcements. Ammunition, replacement weapons, medical provisions, and food all required shipment from Japan, many of which never arrived. Troops stationed in isolated garrisons went months without resupply as submarines sank the freighters that were their lifeline. Battle losses could not be replaced as troop transports carrying reinforcements were torpedoed and destroyed. The Japanese army, which had conquered vast territories and defeated Chinese, British, Dutch, and American forces early in the war, found itself slowly starving in fortified positions because the logistics network sustaining it was being dismantled by American submarines. The home islands faced looming famine as food imports ceased. Japan had never been self-sufficient in agriculture, relying on imports from Korea, Formosa, and Southeast Asia to feed its population. By 1945, those imports had dwindled to a trickle due to submarine attacks on cargo vessels. Urban populations in Tokyo, Osaka, Kobe, and Nagoya faced escalating hunger as rice rations were repeatedly cut. Black markets thrived as desperate civilians paid exorbitant prices for food. Government measures to maintain order were harsh, but the reality was that Japan could not feed its people without imports, which submarines had slashed to unsustainable levels. American strategic bombing, often highlighted in popular narratives and post-war assessments, was secondary to the submarine blockade in crippling Japan's war capability. While the Army Air Force's firebombing campaign devastated cities and inflicted psychological trauma, its immediate impact on Japan's war economy was limited since the economy was already crippled by raw material shortages. Factories could not operate without steel, aluminum, coal, and oil, regardless of bombing. The atomic bombs dropped on Hiroshima and Nagasaki on August 6 and 9, 1945, provided the Japanese government a face-saving reason to surrender, but Japan was already economically and militarily defeated. The nation could not continue fighting because the foundation of its war effort had been destroyed by submarines. The final irony involves the Type 93 Long Lance torpedo, the weapon that had terrified Allied navies in 1942-43 and was cited by Japanese intelligence as proof of technological supremacy. By 1944, as American forces devised countermeasures and tactics to neutralize it, the Long Lance became increasingly irrelevant to the war's outcome. Radar warning systems gave American ships advance notice of approaching Japanese surface forces, allowing evasive maneuvers before torpedo launches. Improved damage control techniques helped ships survive torpedo strikes that would have sunk them earlier in the conflict. Tactical formations reduced exposure to torpedo salvos, decreasing their effectiveness. Most importantly, increasingly assertive American surface forces, backed by overwhelming air power, sank Japanese torpedo platforms faster than Japan could replace them. By 1944, American cruisers and destroyers engaged Japanese surface forces with confidence, leveraging technological advantages that outweighed Japanese torpedo range. American ships had radar-directed fire control for accurate gunnery at night or in poor visibility, reliable radio communications for coordinated fleet maneuvers, and numerical superiority in nearly every engagement. Weapons that should have been Japan's decisive advantage became secondary as American submarines systematically annihilated the merchant fleet sustaining Japan's war machine. Japanese destroyers and cruisers, designed for devastating night torpedo attacks, were relegated to escort duties protecting dwindling convoys, a role for which they were ill-suited. The Battle of the Philippine Sea in June 1944 illustrated the dramatic shift in naval power. On June 19, the submarine Kavala, under Commander Herman Kostler, intercepted the Japanese carrier Shokaku as it recovered aircraft after strikes against American forces. Kostler fired 6 torpedoes at 1,200 yards, 4 hit, detonating aviation fuel and triggering catastrophic secondary explosions. Shokaku, a veteran of Pearl Harbor, Coral Sea, and Santa Cruz, sank in minutes, taking 1,263 crew with her. Hours later, the submarine Albacore, commanded by Commander James Blanchard, fired a torpedo at the new armored carrier Taiho. Initially seeming minor, Japanese damage control officers attempted to ventilate fuel fumes, inadvertently spreading explosive vapors. 7 hours later, Taiho exploded, breaking apart and sinking with 1,650 sailors, including Vice Admiral Jisaburo Ozawa's staff. These were not lucky shots, they were precise, executed attacks using functioning weapons against high-value targets. Shokaku and Taiho represented 40% of Japan's remaining large carrier force. Their loss in a single day crippled Japanese naval aviation at a critical moment. The Great Marianas Turkey Shoot decimated Japanese carrier air groups, downing over 600 aircraft while losing 29 Americans. Submarines had struck first, eliminating vital carriers before American carrier aircraft engaged. Japanese planners, underestimating submarine threats, positioned carriers in waters patrolled without adequate anti-submarine screening, resulting in catastrophic losses. The Battle of Leyte Gulf in October 1944 further demonstrated the cumulative impact of the submarine campaign and the reversal of technological balance. Submarines, guided by code-breaking intelligence, intercepted Japanese center forces. Coordinated attacks sank or crippled multiple heavy cruisers, leaving Admiral Kurita without a flagship, staff, or effective communication at the opening of the largest naval battle in history. The broader strategic impact: the Imperial Japanese Navy ceased to exist as an effective fighting force. Japan lost carriers, battleships, cruisers, and destroyers, while survivors were trapped in home waters by fuel shortages caused by relentless submarine attacks. Yamato's one-way mission to Okinawa ended in her sinking with 2,498 of 3,332 crew. Remaining carriers, without fuel to train pilots or conduct operations, sat idle while aircraft were expended in kamikaze missions. The decisive fleet battle Japan had prepared for 40 years was lost, not due to poor tactics or bravery, but because the logistics system sustaining the fleet was annihilated by American submarines. By early 1945, Japanese shipping losses reached catastrophic levels, making continued war impossible. American submarines, equipped with reliable torpedoes, superior intelligence from code-breaking, and aggressive commanders, sank Japanese shipping faster than it could be replaced. Each month destroyed more merchant tonnage than Japan could build, crippling the economy and strategic mobility. By August 1945, Japan had virtually no merchant fleet left. Those ships that survived hid in ports, too fearful to traverse submarine-patrolled waters. The human cost was devastating. Merchant sailors, civilians aboard cargo ships, died by the thousands from torpedoes, drowning, fires, and exposure. The Imperial Japanese Navy provided no effective rescue, regarding these sailors as expendable. Many American submariners offered aid to survivors, though indoctrinated Japanese personnel sometimes refused it. The story of Japan's dismissal of American torpedo improvements is a case study in how intelligence failures compound into strategic catastrophe. Japanese intelligence misjudged American torpedo capability, affecting decisions prioritizing decisive battle doctrine over convoy protection. By the time Japan recognized the threat, it was too late. The merchant fleet was gone, the economy strangled, and victory in the Pacific unattainable. The American submarine campaign exemplified industrial warfare at its most ruthless, showing that numerical superiority, logistics, and engineering can overcome initial setbacks to secure victory through relentless pressure. Japan's navy fell not in glorious battle, but in the cold arithmetic of tonnage lost versus tonnage built. Submarines, once dismissed as incompetent, became the force that strangled the Japanese empire, demonstrating that wars are won not merely by tactical brilliance but by sustained economic and industrial pressure. American engineering and industrial capacity transformed temporary failures into strategic dominance, a lesson Japan tragically failed to recognize.